Okay, so I suppose we can start. So let's remind ourselves where we were last time. So what did we were thinking about a kind of orgy trajectories. And we had this, this picture of things flowing to the fixed points, and the kind of cartoon of this infinite dimensional space of theories with an action of scaling, and that the theories we're interested in are trajectories which flow to the fixed point in the UV. And we made a definition where a theory is going to be a collection of functionals of a field, they just on Rn, which satisfies infinitesimal orgy flow equation. And together with a locality condition. And we also saw that the set of theories is in bijection with the collection of local Lagrangians which are series in H bar whose coefficients is going to be I just wrote it kind of very schematically. It's a series in H bar whose coefficient is some Lagrangian, i.e. it's an integral of some polynomial in the field of its derivatives. So the important thing is that this is non-canonical and it's scheme dependent. So our goal today is to write down explicitly what is the action of scaling on this side. There'll be some kind of very kind of conceptual and explicit formula for how scaling acts here. And then to transfer it over to the other side, and we'll get something super complicated on this side. So one thing in particular we'll find is that the formulas for the action, once we use these coordinates, here we're choosing coordinates on the manifold of theories. The action of scaling is some vector field on the manifold of theories. And the formula for this vector field in these coordinates will depend on the coordinates. But we can still compute it explicitly in a given choice of coordinates. So how does this work? So let's start by looking at the Lagrangian for the free theory is so I want to write down, I want to make this field scale in such a way that this Lagrangian is fixed, because I want the free theory to be a fixed point. So we let or lambda by of x be lambda to the n over 2 minus 1 by lambda x. So this is how everything will scale. So for any quantity depending on phi, like a functional function of phi or anything like that, so lambda x on functions of phi by just this is the usual way when I have a symmetry of a space, that symmetry acts on functions on that space. This is the usual formula for the action on functions. We could write it as pullback if we wanted. And clearly, this Lagrangian is invariant. Let me put a star there. So we also are interested in how this guy will act on the propagator. Well, of course it's going to preserve, because it preserves the Lagrangian, of course it will preserve the propagator. But once we introduce a cutoff, it will change the cutoff in some way, and we want to calculate how it changes the cutoff. So to do that, we recall that the heat kernel prime is θ minus n over 2 squared over t, so that if I apply this guy to both factors, minus n over 2 but then because I have this prefactor of lambda to the n over 2 minus 1, and this is something which involves two fields, I get another factor of lambda to the n minus 2. So this is the heat kernel T over lambda squared minus 2. I always get confused with these factors. It's completely trivial, but yeah, that looks right, eh? Okay. So if you think about the propagator, well, k t over lambda squared so we can then we can change coordinates to find that this is the integral from epsilon over lambda squared L over lambda squared kt prime t. Okay, so this is some kind of trivial calculation. That the propagator with these cutoffs, I change the UV and the IOR cutoff by scaling them both by 1 over lambda squared. So I want to produce some action of scaling on theories. So a theory is a collection of functionals depending on L. So what should I do? I want to produce a new collection of such functionals. I must, of course, change phi by rescaling it, but I should also change L. So just following the claim. If this is a theory, then so does something I'll call I sub lambda of L of phi, which is or lambda star I lambda squared L. So I rescale my field by lambda, and I also change L by lambda squared. So why is that true? I need to check that this guy satisfies like the Polchinski equation. So it satisfies the infinitesimal order equation. So proof. Well, let's rewrite it slightly, and so let's look at d by dl I lambda L over lambda squared. So this guy we know satisfies the infinitesimal order equation. So I'll write it in this pictorial form. And now we realize that I'm just going to act by or lambda on everything there and use the way it acts on the heat kernel. So I'll bring that or lambda inside. Here I find or lambda star I of L. And here, well, I'm going to apply that to the heat kernel. So I find the heat kernel for L over lambda squared with another factor of lambda to the minus 2. So if you look at this, you'll see that this looks just like the Polchinski equation, the infinitesimal order equation, where I've replaced the heat kernel by the heat kernel with L over lambda squared. And that's exactly what we wanted. We also had a factor of lambda to the minus 2. That factor of lambda to the minus 2 is also what we wanted because of the discrepancy between that guy and that guy. So this is what we want. Okay, any questions about this? Yeah.
Where did the extra factor of lambda power n minus 2?
Right. So the heat kernel is something which lives in the propagator is something that lives in fields, tensor fields. So it acts on each leg. So I hit one guy with land at the n over 2 minus 1. The other one with land at the n over 2 minus 1. So I think I should explain a conceptual point, which I think makes the terminology quite confusing. So the term org flow is used in two slightly different ways. So suppose I'm on some curve manifold. Then there's an org flow where I integrate out the high energy fields and get an effective theory depending on the low energy fields. This will give me a family of effective theories, but each of which has a different field content because I'm integrating out fields each time. And I can't really compare them. You might also, in a similar way, suppose you were studying a lattice model, and you were drawing your lattice on some compact manifold like a torus. I might start with a lattice model with a very fine lattice on a torus. And then I'll integrate out some degrees of freedom. I'm left with a lattice model with a coarser lattice on a torus. Now I can't compare them because they have different lattices. So that's one meaning of the word org flow. But now, if I'm on flat space, there's an extra step I can do. I could start, so from the lattice point of view, I could start with a very fine lattice. I could integrate out some degrees of freedom and be left with a model for a coarser lattice. But then I can rescale to bring myself back to the fine lattice, and I can compare to what I have. So this integrating out and then rescaling back to what we had before, that's the procedure that gives you these org trajectories. It's only something we can only do on flat space. So we're seeing that here. These I of L's, as L varies, that's the kind of integrating out piece. And this rescaling allows us to compare them. So this quantity here, I've integrated out and then rescaled to bring myself back into something where I can compare them.
Does rescaling also work for conformal field theories?
Well, conformal field theory is one, say from the lattice point of view, where if I integrated it out and then rescaled, I would get back to what I started with. So from this point of view, the thing over there and the thing over there would just be equal. So now we understand the flow on the space of theories. We start with one theory and then we produce a new theory by that formula. So we define the or greater than 0 action on the space of theories by I of L gets sent to I lambda of L, which is or lambda star I of lambda squared of L. So if you think about it, what does this mean? So if I start with my original theory, let's say my original theory at some large scale, where the interactions are in some region of size 1, those interactions are the same as the interactions of the rescale theory at some very small scale, regions of size lambda, where I've also scaled the incoming things, the incoming fields. So this is a little bit abstract. And you can ask, how would we actually compute it in practice? So to do that, we need to say, let's choose a scheme, and we'll choose coordinates using the scheme on the space of theories. And then we can get a formula for this action. So if we have a scheme, we can write. So a scheme is a way to choose counterterms. So here I is going to be some h-bar dependent Lagrangian. And I, C, T, epsilon. These are the counterterms. And these are uniquely determined by this scheme. So uniquely determined as long as we ask that they are purely singular. As functions of epsilon. So what purely singular means, our scheme tells us what that means. Log is purely singular. So so if we apply this formula to this expression, we can kind of bring it inside here, and we'll figure out what it does to this piece. So, or lambda star I lambda squared L. Oh, and just to remind you, this W gadget, that's just a notation for sum over Feynman diagrams where this is the propagator and these are the vertices. Now, I can bring this rescaling inside, but I have to hit everything inside with this rescaling. You know, I'm rescaling everything in sight, so I can move it I can write it like this. I must rescale what happens on every edge. And at every vertex. Now we know what this does to the propagator. It shifts epsilon and L by multiplying them by lambda to the minus 2. And finally, we notice that because I'm taking the limit as epsilon goes to 0, I can just change variables to define my new epsilon to be lambda minus 2 to the epsilon. So it will look just like what we had before. that right, or is it lambda minus 2? Yeah. Okay, so this looks just like what we had before, except for this lambda squared epsilon appearing here. So let's think about these counter terms. Well, these counter terms are not purely singular for the scheme we had before, but they're purely singular for a new scheme. So I C P lambda squared epsilon are purely singular for a new scheme where f of epsilon is singular in the new scheme if f of lambda to the minus 2 epsilon was in the old scheme. So what we're finding is that this orgy flow, what it does, once I choose a scheme and choose coordinates, it just rescales my Lagrangian that gives me the coordinates. This is the naive part. But it also changes the scheme. So let's write this out a little more formally. So unless there are any questions.
Find a choice between singular functions that is invariant under the same scale.
It might be. That will happen if you have a CFT. So as an example, suppose we choose if you know, kind of epsilon to the minus k is purely singular, then so is, you know, lambda squared epsilon minus k still is. Because it's just. So things like this will not change, but if log epsilon is purely singular, then log lambda squared epsilon is not. So what you'll find is that the things you'll be messing around with will be things which are not polynomial. They look like log or integrals of log. Those are those functions which will be singular in one scheme, but not in the other. Yeah.
So what about log epsilon?
Log epsilon. I'd have to think about it. You know, I suppose you'd have to think about that. You know, if you change it, it becomes log of log epsilon plus 1, or log of log epsilon plus lambda squared, and then we should. Yeah, I'm not entirely. Things get pretty tricky at two loops, and this should be a two-loop thing. Okay, so let's try and write out little things a little more formally, just to get some more clarity. So I'm going to write A as a class of real analytic functions you know, I say real analytic. In practice, only some kind of countable space of functions will appear. Everything that appears here will be some iterated integrals of rational functions. So it's nothing too crazy. A plus those functions where the epsilon to 0 limit exists. A scheme, a choice of A minus, which is complementary to A plus. This group acts on A by sending f goes to f of lambda squared epsilon, and it preserves A plus. Therefore, this group must act on the space of schemes. So if psi is a scheme, it should go to or lambda psi. Now let's use. We're going to use another. Going to write out more formally another piece of data, which is, a scheme gives us a way to identify a Lagrangian with the theory, but that identification, two different schemes, that identification will be different. That gives us some change of coordinates in the space of Lagrangians. So we let S psi be the identification between Lagrangians. So S psi 1 inverse S psi 2 is going to be some crazy change of coordinates in the space of Lagrangians. And what we find, so just a more formal way of writing what we saw already is that the orgy flow so the orgy flow action on the space of Lagrangians sends I. So what do we do? First we rescale I, but we also have to change the scheme. It's something like we rescale a Lagrangian and then we implement the change of scheme isomorphism from the scheme I started with to the new scheme. So this can be a pretty complicated thing and understand it written pretty abstractly. Next I want to compute what happens for the phi-4 theory. Any questions? for the algebraic geometers in the audience, like there seems to be some very interesting algebraic geometry concerning what a scheme is. I mean, some people study them using degeneration of mixed Hodge structures because these guys are period integrals of varieties which degenerate at epsilon equals 0. And I believe you can study them by looking at the limiting weight filtration and things like that. I think there might be some interesting math in that direction. I don't understand it. Okay. So let's see what happens for the 5-4 theory on OR4. Okay, so this or lambda of phi is, in this case, lambda phi lambda x. So you can check that integral of phi 4 is fixed by this rescaling. Just because there's 4 of them and they shift dimension 1. So classically, now to figure out, we're going to figure out, I'll put a constant here. We're going to figure out what's going to happen at one loop. So to understand what happens at one loop, we are going to have to write down the one loop counter terms and see how they change when I change the scheme. So we'll start with a scheme psi where epsilon minus n is singular and log epsilon is singular. So the one loop counter terms so we already computed them for the phi cube theory, but actually they're the same. I mean, it's the same computation. So this diagram gives you something of the form epsilon minus 2 integral phi squared times c, where c is the coupling constant appearing next to the phi-4 interaction, and c because there's only one vertex. Whereas this diagram, this one is logarithmically divergent, and we computed that this gives you c squared log epsilon integral phi-4, and that there are no other one loop counter terms. So what we're supposed to do is we're supposed to scale epsilon and see that it can be rewritten as a Lagrangian including a new term at one loop with some purely singular counterterms. So if we send epsilon to lambda squared epsilon and apply or lambda star, then integral epsilon to the epsilon minus 2, the integral of phi squared. At some point, I might have mixed up lambda and 1 over lambda, so let's not worry too much about that. So what happens here? Well, here I pick up a lambda to the minus 2, but here I should pick up a lambda squared, because phi is of dimension 1, and I'm integrating it in 4 dimensions. This is fixed. So what we find, as we saw must be true, is that counter terms, which are polynomials in 1 over epsilon, can never contribute to the orgy flow. They can never contribute to the beta function. So, well, okay. Whereas this guy, integral phi fourth is unchanged under rescaling, but log of epsilon, I'll pick up a log lambda squared term. Remember, this is a one loop, so this will be accompanied by a factor of h bar. Now, so we see that the effect of scaling lambda is to introduce a new finite part which does not depend on epsilon. So we have the same theory with the same scheme, but with this new term appearing at one loop. So we're kind of doing this calculation in a slightly implicit way. So we're changing schemes by changing epsilon, and then figuring out what Lagrangian in the old scheme will reproduce the effect of the original Lagrangian in the new scheme. So, the conclusion is that the one loop orgy flow sends this Lagrangian to the same one by fourth plus c squared log lambda squared h bar. Where we're describing on both sides, we describe everything in the scheme where log epsilon is singular. So just to reiterate, if we decided, so it's, to compare things, we should really make sure we're on with the same scheme. So the thing on the right-hand side is equivalent to the thing on the left-hand side in the scheme where log lambda squared epsilon is singular. But then rewriting that in the scheme where log epsilon is singular, we pick up this term. Okay, any questions?
So it's almost something we just sort of we did urgent flow, we got something, and then we changed basis back to the original scheme. That's the expression we got.
Exactly, yeah. Yeah, because like in the scheme where log lambda squared epsilon is singular, this whole gadget here was the counter term. But in the other scheme, well, this only this can be the counter term, so this has to be a new term of the Lagrange.
So when you say one loop RG flow, what you mean is like do the RG flow and then just kill off everything in each part square.
Exactly, yeah. Is that, yeah. I actually wouldn't, I know in theory I know how to calculate beyond order h bar, but in practice I don't, so.
In practice, how often do you ever need to calculate beyond order h bar, or is order h bar good enough for most purposes?
Order h bar is good enough for most purposes. So what you can show is that the order h bar, if you start with the theory which is fixed classically, then the order h bar term is always scheme independent. So it's the only term that's really meaningful. So this is something that should be familiar from obstruction theory. This is the first obstruction to being conformally invariant. So that's always some. There'll be a deformation of the classical theory given by its obstruction to being conformally invariant, and this is that.
So what kinds of questions would you ask about this one loop term?
Yeah, great question. So it's super important actually. So because let's think about it. So if we think it's going to be in some sense a dominant term. So if we think in this picture here's a fixed point. We're in free theory. We can choose a basis of the tangent space corresponding to some basis of Lagrangians. So in this basis, the or greater than 0 action will be some vector field and it will look like the Cn is going to be the coordinates and this is the dimension. So the leading term will be just, it just scales everything linearly, plus. And what we've computed is like the subleading term in the fixed point directions. So if, say, C0 is the phi to the 4th Lagrangian, plus h bar C squared. it's a c squared because you get a c squared there. So, like, for instance, if you just look at the directions which are fixed point directions, this gives us the subleading term. And the higher loop terms will give you the higher powers at c. But you really care about what happens near the org fixed points. And there, this is the dominant term. So when people want to prove asymptotic freedom, they say, well, we have these higher order terms. I have no idea what they do. But if I just look in this direction given by the direction which whose leading term is fixed, to figure out whether I'm pointing inwards or pointing outwards, I just have to compute the subleading term. So the one loop term is exactly what tells you which way you're pointing at the fixed point.
But if you have like multiple fixed points, like in QCD, where principal is going from the prefix point, back sax point, and so on.
To the which point?
To the IR, back sax point, if you have the right kind of model, then you probably do need like the higher order terms as well.
Yeah, that's absolutely right. So if you want to like figure out analytically what's going to happen at the other end of the trajectory, you need to resum everything. So of course that's in practice that's completely impossible. So you can So people believe there are other fixed points, but I don't know. Do they have numerical evidence? Like Feynman diagrams are not going to get you to another fixed point.
Yeah.
So here we come to kind of an annoying point. If h bar is a formal parameter, you can't really tell which direction it points, right? Because so if we look at this expression and you say, well, what happens when what happens if I'm over here and I kind of flow this way? I'll find, well, this term will have some logarithmic growth, so we'll go off that way, but pretty slowly. When I flow to infinity, it will also have logarithmic growth. So we're never really going to be able to see this nice. It's pretty difficult when h bar is a formal parameter and you're working in perturbation theory to see this nice picture of things converging to a fixed point. So kind of as a kind of a hack, you can say, we'll say a theory is perturbatively renormalizable if I lambda of L has logarithmic growth as lambda goes to 0. So this is a situation, you don't actually know when you set h bar to be a number. Like, if we set h bar to be a number, this h bar to the lambda, if I expand it in series in lambda, will have terms involving log lambda. But if h bar is a number, this may or may not behave well. It's not going to 0. Sorry, lambda to the h bar, sorry. Yeah. Lambda to the h bar may or may not behave well as lambda goes to 0. This is kind of a slightly hacky way of dealing with these subtleties. But it allows us just to talk about So for the phi-4 theory, you think, well, now can we cut down our infinite dimensional space of fields? So you can show the set of perturbatively renormalizable theories is given by things like the series in H bar with the coefficients the only coefficients we're allowed to have are the phi-4 and phi-squared terms, as long as we impose all the symmetries. So now, so in some sense, we've achieved our goal of finding a nice subset of the infinite dimensional space of theories by saying, well, we just look at those theories that when we flow, we only find logarithmic growth. If I tried to add on something involving phi to the sixth, I would find polynomial growth, and I would spoil this feature. But at each order in H bar, I'm free to add on anything like that.
But in terms of, you sort of say, instead of renormalizing theories, which is compatible symmetries, that you've done something that at each stage is not, of like perturbation theories is not compatible with symmetry. But if you were able to take the full theory.
I kind of see what you're saying from, like, if you had symmetries which was some non-reductive group or something, but here the symmetries are really simple. SO4, it's reductive, you can't really. SO4 and also the Z mod 2 symmetries and phi to minus phi. I wanted to preserve that. No, there's anything else you could say. So maybe more generally, so the set of perturbatively renormalizable theories is equal to, again, non-canonically, the set of series in H bar whose coefficients are Lagrangians of dimension less than or equal to 0. So either those that are fixed by scaling or those that have like negative 8. Right. And you could, if you wanted, also have the condition that when lambda goes to infinity, you have logarithmic growth. That will exclude those things of negative dimension. So this is something that's true quite generally. And yeah. Okay. Yeah, maybe I'll stop there unless there are questions. Maybe next time I can do some more examples and start to introduce gauge theories.
If coefficients were Lagrangians of dimension 0, is that the same here?
No, because you still have this. That's something where it would be classically conformal, but these quantum effects spoil that by introducing this logarithm. So it's almost impossible to write down a Lagrangian for which is a fixed point at all orders in function. You can only, I mean, in practice, you can only do that if there's some kind of magic hidden structure.
So the situations where I'm most familiar with data function computations is like for like a 2D sigma model where you calculate a wave function to find out it's like the Ricci curvature.
Yeah, I was going to do that example next time.
Okay.
Super easy.
And also this thing that you mentioned of how, if you want to know what's happening at the other end, you would have to do some sort of non-conservative business, which is like totally impossible. Is there any, I know there's some people now who sort of survey Foucault and so forth who are using this resummation, resurgence, find non-conservative effects from resumming in a clever way. Is that sort of something that you can do from this point?
I don't know how to do it. It seems really interesting, but I mean, it's if you think about the path integral, you'll see finite dimensional analog of the path integral will lead you immediately to thinking about things like vanishing cycles. So people have thought about maybe spent some time. I think this plays a role in that stuff too. Like, what's the infinite-dimensional analog? What are the Stokes phenomena as you vary h bar in the complex plane, or the Stokes waves? And I think that's, it seems really, really fascinating, but I don't understand.